Hello and welcome back. Let's discuss a bit how we can do classification tasks with machine learning. So what is classification really? We want to discriminate between two or more classes like cat or dog, or in a commercial word, between a transaction that is fraudulent or not. Or in materials research, for example, what kind of damage we have and where we have damage in the steel sample. Essentially, from a statistics perspective, we do hypothesis testing. In our simplest case, we have two classes and we transform our data into a probability for each class, and this is called a test statistics. And in the best case, those two classes and the associated probabilities are well separated. So class 1 has nothing to do with class 2, and we can easily place a discriminator between them. So in the best case, we split the data in training and test data, run the training and the test data with our classifier, and then we have the true assignment, class 1 and 2. They are known, and this is our fully labeled data set. Say one class is the negatives, for example, we don't have any damage in this class, or class 2 is positives, like we have damage here. So in the ideal case, we've just discussed this, there is no overlap in the prediction between those, and the classification result is always correct. Of course, you might have guessed that in reality it's not quite so simple. Classes can be quite difficult to distinguish, like kitten or ice cream, parrot or guacamole, sheepdog or mob. There are some funny memes on the internet, but more seriously in our applications we will be faced with the same conundrum. Some of the cases will be very difficult to assign to one or the other class, and we will need a lot of expert knowledge to make a guess. So this is where we need the prediction as a probability. We need to be able to quantify how sure we are of our result. So that means essentially all classification results need to be interpreted as a probability. This also depends on the use case. What do we capture more events even if we are unsure, or do we capture sure cases? This is also something that we need to decide when we build our training data set. Do we only use, for example, textbook examples, but then we introduce a bias because most realistic cases will be slightly different. So in a more realistic scenario, those two class predictions will slightly overlap, because at the end we wouldn't need machine learning if it was that simple, right? So we need to define a cutoff between those two classes, and as you can see from the illustration here, the prediction for class 1, for example, not damage, and class 2 damage will overlap. So there will be regions where our machine learning model or our classifier in general will not be able to distinguish between them perfectly. So when we define a cutoff and everything above a given probability is now classified as class 1 or class 2, we make two types of errors. We can either accept class 2 even if it was in reality class 1, this is called a false positive or a type 1 error noted by alpha. Or we accept class 1 even if it was class 2. This is called a false negative or type 2 error denoted by beta. So how do we choose this discriminator, this cutoff value TC? There is no general answer to this, and it depends on your use case or application or research project. So this is what makes it quite important to consider exactly what we want to achieve with our classification result. Now let's come back to this illustration, but now a more realistic case. The predicted probabilities overlap, so that means the prediction is not always resembling the true class. So we can have true positives, they are known to be true from the label and identified as true. We can have false negatives, they're known to be true but identified as false. We can have false positives, known to be false but identified as true, and true negatives, known to be false and identified as false. And we also have the sum of all positive ones known to be true and all negative ones known to be false. These are essentially the labels in our test data, for example. And now, because the model isn't perfect, we can see that these two classes mix. And one way to classify how often we make the kind of mistakes, we look at the confusion matrix. So on one axis we have the prediction, and on the other axis we have the true labels. And then ideally we want our results to be on the diagonal, like the true positives and the true negatives, and the off-diagonal elements should be as small as possible. Another way of identifying how well a classification machine learning model works is to use the ROC curve. Remember that we, at least in principle, need to interpret everything as a probability. So we can vary the cutoff rate, TC, and then we can evaluate how well this machine learning model performs. Again, we can use this also to determine the best threshold, and that depends on the application. We need to decide what kind of hurts us more. Are false positives more harmful to our application than false negatives? And the ROC curve gives us a nice illustration of how the model behaves. It's named after the receiver operating characteristic from radar screens, and what we essentially do is we vary the threshold TC and observe the outcome on the false positive rate and the true positive rate. The diagonal line on this plot corresponds to random guessing, and everything below this is even worse than guessing. And the ideal point is in the upper left-hand corner, where we have always correct results. Of course, in a realistic model, this isn't quite achievable, but the curve will show us how close we get to this ideal. If we have multiple classes, we need to normalize the output, and this is done by the so-called softmax operation. This sort of converts the prediction for each class into a score that sums to 1. If we have a well-calibrated model, we can interpret this as a probability for the n classes. And again, we now set the threshold, similar to before, but now for the n classes. And we can also extend the confusion matrix for this application.